This doesn't help me. I need... Now, you're supposed to preload the lecture that I'm going to give, not the one I gave.
Go to PDF, it's in the same folder.
I am in PDF.
The last page is probably in this content.
How do I get the cursor to go down? Why?
I don't see the scroll bar.
זכרת שבשתיים נערך לפגישה עם
אני דחיתי את, החלפתי עם...
אז
הוא מגיע ב3 פה. No, I don't see...
Let me try. I don't know why it doesn't appear.
I'm definitely getting an apple.
You're using...
It's not better than this.
So you're taking
Page number 30. Okay. This page. Select all and copy.
No, I want to go up. I want to go up to the previous page. Alright, this is
Oh no,
fucking
here you
impossible.
have this tab here. Okay. One page for the not even before. You discussed this yesterday.
Now, how do I get down? How do I get down to the bottom of the page, for God's sake? No, I'm getting a Mac, that's all there is to it.
Let me try it. No, it doesn't appear.
Alright, you know what? I'm going to use this.
Select all and this page and paste there.
Alright, I'm just going to use the mouse to scroll.
Oh, okay. Nice.
Rahul, I don't have to do this during the lecture. I want you to do it before the lecture.
Going to copy and paste.
Alright. In the electron frame, everybody know how to calculate inverse Compton, Thomson, inverse Compton scattering. Let's talk about Thomson scattering. You can do it classically. The electron oscillates. The electron oscillates with this, according to this equation. The dipole moment is E times x. D is the dipole moment, and therefore the power radiated is this. E 2/3 E squared A squared over C cubed. A is x double dot, 2 squared D squared over C cubed. So you compare the power radiated to the incident flux, and you get a cross section, and it's this. It's the Thomson cross section, and if you have a relativistic electron, you go into the frame of the electron. If the photon is still much less than the electron rest mass, you can ignore recoil
Okay.
and treat the photon as a wave. But the k vector for the photon transforms like a 4 vector,
Okay.
a contravariant 4.
For
No, it's sorry. It's this is actually a mistake. It should be the mu should be underneath, right?
Yes.
Because it's a
Covariant.
covariant.
Okay. And this k would be a vector sign. Omega by c and
I mean, you can have k with the mu on top,
minus will be there.
but then it would be minus omega.
Minus omega c.
Okay. Anyway, this is the transformation matrix for a Lorentz
Lorentz boost.
for any vector in special relativity. Basically, for example, x.
K is a vector there.
What?
K. It's not covariant there. So it was okay.
This was x, right?
This is a vector.
This is a covariant.
But it depends how you write. We can always change things.
No, but
I think
dx
Yeah, but I think
transforms like a contravariant vector, right?
The vector, unit vectors transform like contravariant, and the
Yes.
coordinates transform like covariant. So
What do you mean the coordinates?
the component, let's say.
Understand what that means? Dx mu
Yeah.
is the distance. It's the
That's-
proper
That's like unit
distance. It's a vector, and it transforms. Let's put it this way: x mu prime is equal to gamma times x minus v. Now,
Because
the
you
question in
wouldn't
special relativity is always, what does this mean? And there's no way I'm going to remember it.
Because you wouldn't get k nu x nu is a Lorentz invariant.
That's right.
Because of that, it's a big k nu, the superscript.
That's right. It is.
Yeah. This is also an k. If k is below then and x up, then it's also.
I mean, this. I didn't say if it was covariant or contravariant here. I just
Yeah.
said it transforms like a 4 vector. But the only way to keep the science straight that I can see in special relativity is to work out a simple example in your head. Like if x is, if it's moving this way in the lab frame, and let's say this is the positive x direction, so it's moving this way. So x minus vt, because t is positive and x is positive, is 0. So I know that if x prime remains the same in frame, then if this is 0, then this will be 0. So it remains at the origin. And then I look at this, and yeah, there's a minus here. It's
I don't know where
gam.
it's turning
If I took x,
Simply put gamma equal to 1 and then it must transform to Galilian.
that's right.
Yeah.
That's right. But, so the only question here, I can also write this as gamma x minus gamma. And by the way, there's a.
Yeah, that would be nice.
It's v over c
And
times
this is
ct, but it's gamma beta. If c is equal to 1, then we can just write x and p. So you see here, it's gamma minus gamma beta. If I wrote it in matrix form, it would be gamma. Okay, now here I wrote the mu here. Why don't I write prime here and unprime here?
Then prime will be up on this boost.
So that means it's minus beta gamma here, minus beta gamma here. Now, the inverse transformation, it's the same gamma, you reverse the sign of beta, because the velocity is just going the other way.
Right.
And the whole point is the gamma squared times 1 minus beta squared is equal to 1. And so if you just do it once with plus beta and once with minus beta, you get back to where you started.
Okay.
So that boost x mu prime is equal to lambda mu prime and below 1 will be mu.
What?
No, you're saying it's prime and
Because it's the inverse of x mu prime is equal to lambda mu prime.
The inverse of this is switching the mu and the mu prime, right?
Yeah, but then you have to write mu inverse. Otherwise, it's
That's
not
right. But if I switch mu prime and mu, I would switch minus the plus here, right?
Yeah, that's true. But this transformation matrix cannot basically correlate unprimed coordinate and prime coordinate.
It cannot what?
Correlate. I mean this.
Why not?
Because this has to
Cannot
be,
connect? You mean?
yeah, this should be like this, I think. I mean, I think. Then it's
Oh, right. Oh, I see what you mean.
yeah.
Right. So this is prime and this is unprime. Because the unprime, if you want to make the unprime go away, you have to have one bottom and one top. And in that case, I didn't put either one here,
Yes.
but I need the prime on top because I have the minus. Okay.
no, there you don't have to. You're using mu and mu, so that's okay. You just have to use two different
Yeah,
symbols.
yeah. Mu prime is like mu and same thing.
Well, all right. You know what? I'll make it mu prime here if you want, but no. The point is, this is a mixed
Yeah.
tensor, and when I wrote it here, I meant this.
Yeah.
Okay. The next thing on the agenda seems to be Doppler shift. So again, you just transform into the electron frame. Oh, now we're still calculating Compton scattering. In the electron rest frame, I took, for example, 180 degree reflection, so K goes to minus K, but omega stays the same, still in the limit of elastic scattering. And then finally I transform back into the lab. So I transform into the electron frame, then I made the scattering in the electron frame, and then I switch back. So it's 3 stages. So omega triple prime, when all is said and done, if you work out the Lorentz transformations, is equal to this.
Mm-hmm.
And K is, as usual, omega over C. Well, minus in this case. Now you can show that one thing that stays the same, just by chance, is the emitted power.
Okay.
If it's emitting in the rest frame, if it's emitting isotropically in its own rest frame, and you have to say isotropically, then in any other frame it'll be emitting the same amount of power. Because now the photons in general will be more energetic.
Okay.
Because let's assume it's emitting isotropic, and then you have a Lorentz boost. On the average, the photons are multiplied by gamma.
Okay.
And here's where the assumption of isotropy in the rest frame comes, because if we're emitting backward, then transforming forward, they would lose energy.
Yes.
Because it's opposite to, and if they were going forward and you transform forward, I think it would be like twice as more than gamma. It would be up to 2 gamma.
So why it's
But if it's emitting isotropically, then on the average it's just gamma. You're multiplying the energy of each photon on the average by gamma.
Okay.
So it's emitting the same photons, but they're more energetic. So how could the power be the same? The answer is because more time is elapsing in your frame than in the rest frame, by a factor of gamma. And that's basically what this proves. The main thing is that you have to integrate over the main thing is you just have to integrate the what Are you sure? Oh. I pasted it here.
No.
There. So this calculation just tells you, dW is gamma dW prime, and dt is d tau is dt over gamma. So the invariance of so the emitted power is the same. Now, I don't know why I had to go through all this, but the number of, if n is the phase space density, then the number of particles per unit phase space is obviously also a Lorentz invariant.
Mm-hmm.
And I don't know why it's necessary to do this. If dWt is equal to dW prime d tau, that shows that the power emitted is invariant.
Yes.
And it means you can calculate the this should be Auer synchrotron radiation in the frame of the particle, and then you'll know what it is in the frame of the observer. In astronomy, you want to know how much power is being radiated. You're in the observer frame, but you can calculate it in the frame of the particle, and it's the same. And I think all this now is just to get the factor of 4/3. The idea now is that if you want to calculate the rate of photon emission by the rate of inverse Compton power in the bath of photons, you can calculate the energy of the bath of photons in the frame of the particle, and then just calculate.
So why this Thomson cross section?
And that's assuming that in the lab frame it's isotropic, as we'll see.
Why this Thomson cross section is coming here? This inverse Compton.
Because I'm assuming it's Thomson scattering.
Oh, okay. So
It's called inverse Compton because the photon gains energy
Yes, yes.
instead of losing energy. But it's really
Oh,
but that's because Compton discovered recoil, whereas Thomson didn't think about recoil. But when it gains energy, you don't have to worry about recoil because but they still call it inverse Compton because it's gaining energy instead of losing it. So the point is, okay, so this was for the photon bath. The photon bath is the density of photons per unit energy. You have to be careful here. It's just the this has units of number of photons per unit energy per unit volume. That's the dimensions of the left-hand side.
Okay.
No, it's not per unit energy because it's multiplied by dE. It's multiplied by dE, which has units of energy, so this cancels that. So it's number of photons per unit volume. N is the phase space density, which is per unit volume, per unit momentum volume. But since I'm multiplying by dP, this also has, it's just a spatial density. And the idea is that the phase space density is a Lorentz invariant because d cubed p d cubed x is Lorentz invariant, and certainly this is just the total number of particles. It doesn't have any unit, and not anything without units is Lorentz invariant. And what's not proven here is that dqp over E is also a Lorentz invariant, and you can see if you just go into an axis where the perpendicular axes are unaffected by the Lorentz transformation, and for a photon, which is massless, the parallel momentum is just proportional to the momentum is just proportional to energy. So dE actually I'm lost here. So the point is the energy density. I said the photons had a factor of gamma more energy, but for inverse Compton, you have to take into account the fact that when you transform into the particle frame, the energy density of the photons has changed.
Because of space contraction?
Yes, come on in. Hi. Okay, class is over.
Okay.
Yeah, we'll continue.
Miniature class.
Continue next Wednesday
By
at
2
2 o'clock. And if I'm late, because I'm going to lunch with somebody, I'm late. But Wednesdays we have lunch actually, so nobody's late. Never mind. We can always meet at 2. Okay.
Sir, can I get this one, because I will write the corrections etc. in the text.
Yeah, you can get it in after the colloquium. I want to talk to the speaker now. Yeah. Come on in. Yeah, come on in.
But there will be some refreshment downstairs on making meat.
What?
Some cookies and stuff.
Yeah. Oh, refreshments.
Refreshments that students will finish. So.
Okay. Familiar. So I finally I have.